Hello, everyone. Today we're going to be doing some R code that corresponds to section 2.1 from Statistical Methods for Rates and Proportions. So I'm going to start out by setting some of the variables to be similar to the example seen in 2.1. So we're going to have a fixed number of trials of 25. We're going to have a fixed probability of success being 0.75. Q is our probability of failure, which is equal to 1 minus P. And we're going to be specifically looking at X being observed at the value of 23. So we have a binomial distribution where we want to talk about the number of successes in a fixed number of trials. And we can first start by running this in. So now we've defined N, X, P, and Q. So to start, we want to calculate the probability that X equals 23. And similar to the formula in the book, we could just hand write out the binomial formula to be the choose in X, P, probability of success to the number of successes, and then the probability of failure to the number of failures. And if we run that through, we see that we get a probability of about 0.025. But there's a shortcut in R, so you don't have to write out this complete formula if you don't want to. You can use the d binom shortcut. And in this shortcut, you're going to tell R how many trials you have, so that's N, the probability of success, which is P, and then the observation of 23. Okay, so if we run that, we should get the same exact thing, 0.025. So really it comes down to preference if you want to have to write out the formula or if you would like to use the R shortcut. I personally like the R shortcut for myself. Now, we might like to calculate the probability that X is less than or equal to 23. So in our case, we could use, like always, a few different options, which would be that we could calculate d binom from 0 all the way up to 23, where we have 25 trials and the probability of success being 0.75. And we can sum that up on the outside. And if we do that, we'll get the 0.9930. Now, there's an R shortcut once again, which is P binom. So P binom is slightly different than D binom because P binom is telling you the cumulative distribution up to 23, whereas D binom was giving you the exact probability that X equals 23. So that's the difference between D binom and P binom. When we run this, we should get the same exact thing that we got. So whether you use option 1 or option 2, that's really a matter of style. I like option 2 just because there's less things to type. But it's a good exercise to do both so that you can see the relation in what the functions are doing in R. Now, a third thing we might want to calculate is the probability that X is greater than or equal to X. Well, in this case, once again, we can use two options. We could use D binom, and then we can focus from X up to N, so 23 up to 25, where we have a fixed number of trials at 25 and a probability of success of 0.75. And then we could sum all those individual probabilities up and we get 0.032. And similarly, we could use P binom, but we have to think about this real quick. If we want the probability that X is greater than or equal to 23, and that would be similar to 1 minus the probability that X is less than or equal to 22. So that's why I'm using X minus 1 right here for option 2. And if we run that, we can just prove to ourselves that we get the same exact thing, 0.032. Now, rather than having to think about what's the probability that X equals 23, and then someone says to me, what's the probability X equals 24, and so on and so forth, we can combine this all together. And so when we have a binomial type of problem, we could say, well, I know that the smallest number of successes I could have would be 0. And the largest number of successes I could have would be the number of trials, in our case, 25. But if I have 0 successes, that means that I would have 25 failures. So I could set up T as just a table that would tell me my number of successes and number of failures. So let's look at that real quick. And we see that when we have 0 successes, that means we have 25 failures. If we have 1 success, that means we have 24 failures. All the way down to when we have 25 successes, that means we have 0 failures. And then we could set up the PDF, the probability that X equals one of these numbers, the CDF, the probability that X is less than or equal to the number of successes. We could calculate the probability of being greater than X, which the CDF and then the probability of being greater than X, that should add up to 1 for each of those. And then we could also think about what's the probability that X is greater than or equal to some observation. In our example, what's the probability that X is greater than or equal to 23? So I've programmed each of these things. The PDF is going to use the D binom function. The CDF will be the P binom function. The greater than X is also going to use the P binom function. But in reality, since we want it to be greater than X, we're going to say lower tail equals false, which means upper tail is true. So we're going to get the probability of being greater than X. And then at least X, remember, like before, we're going to have our number of successes minus 1 because we're using the law of the complement to be able to calculate these things. Now, R ignores white space, so it doesn't matter that I had to use 2 lines here to code this, whereas before I put everything on 1 line. So just a heads up on that. So if we run all this, we can now look at T, a little more detail. Okay, so let's look at our example of 23 successes. That means that there's 2 failures, and the probability that X equals 23 is 0.0251. And the probability that X is less than or equal to 23, that's 0.9930. The probability that X is greater than 23 is 0.0070. And the probability that X is greater than or equal to 23 is 0.0321. So now, since I set up this binomial table with all the information that someone could ask me, then it's just a matter of going to the correct row for the number of successes, figuring out what they're asking for. If they want the probability of a certain number of successes of exactly 23 observations in that fixed number of trials, then you can get that 0.0251 and so on, just depends on the question. But I really like creating this table because then I get to see everything at once. I could also plot the number of successes versus the PDF, right, to get an idea of what the density looks like. I could look at the cumulative distribution function to see once it starts at 0 and goes all the way down to 1, right? And I can get different information from each of these columns, so that makes it nice. I'm glad that you got to watch this video, and I hope you learned something about coding in R and the binomial distribution. Have a great day.